Welcome to the Databricks Skill Builder series. We're glad you're here. All right. Thank you for joining today, everybody. Today we have TJ, who's one of our specialist solutions architects, joining us today, talking about MapInPandas. And so if you have any questions, go ahead and feel free to drop those in the Q&A box. We have Dallas with us today to help answer questions. And then if your question is better to be asked out loud, go ahead and raise your hand and we will unmute you at a good time to ask your question. And with that, I'll pass it over to TJ. Thanks for being here today.
Great, thank you, Stephanie. Welcome, everyone. My name is TJ Saikota. I'm a specialist solutions architect with Databricks. And we have a very exciting topic for you today around this feature called MapInPandas, which is one of the lesser known features in Spark. And the context for today is basically how to process or ingest any file type. So these are kind of lessons from the field that we think are broadly applicable to a lot of organizations. So let's go ahead and dive in. So the basic setup here is when you're working with Spark and you need to do some type of transformation, there's several different approaches you can take. So with one-to-one mappings of one input row to one output row, every Spark developer knows this, is you should most of the time be using a out-of-the-box Spark function, right? It's performant, it's parallelized, it will work best for 99% of the times, but sometimes there's times where you'll need to use a custom user-defined function, and that's fine too. There's other types of operations where you want to transform one input or many input rows into one output row. So typical group by ag will work. And then if your transformation is actually a more complex aggregation, or you're training many models in parallel, like we see a lot in machine learning use cases, there's also apply in pandas. But our focus today will actually be on this last step, which is how to essentially explode one input row into many output rows. So there is a Spark function for this called explode, which will handle this. But there's a lot of times where this doesn't quite cover it, or it's not the most performant way to do it. So we're going to explore this other approach called MapInPandas. So to kind of give some background, MapInPandas is a function introduced in Spark 3 that does a data frame to data frame mapping. And if you've used the Scala dataset API or PySpark RDD API, it's similar to a flat map operation. And importantly, MapInPandas is not to be confused with PySpark Pandas, Pandas map or apply map, or Pandas user-defined function. So Pandas is all over the place, throughout Spark, throughout Python development. So we just want to call out that what we're talking about today, MapInPandas, is slightly different than all those different approaches. But what we'll go through is a couple of examples of how to use that on real tangible use cases. I kind of mentioned on the previous slide, there's another function that you'll see a lot of times, especially for groups model training, called apply in pandas. But the whole premise of MapInPandas is it allows you to efficiently complete arbitrary actions on each row of a Spark data frame and yield more than one return row. So this is super powerful for a lot of use cases. And the reason we wanted to have this session in particular today is because it's not very easy to get started with it. There's not a lot of good examples online. The Spark documentations are a little rough around the edges on this, since it is relatively new. So we wanted to give some helper examples or some tangible code examples that help illustrate how MapInPandas can be used. So let's start from the basic. What does a basic MapInPandas function definition look like? So I'm going to kind of walk through the function definition, or kind of a signature for it, and then we'll go through a really basic example and then move to a more sophisticated example. So the premise is it's a normal Python function. You define it with a def statement. Right? So define your function name, and then with a colon at the end. And what it's going to take as an input is an iterator of pandas data frames. Right? So this is kind of a new concept. Right? If you know a Python iterator, basically what you're iterating through is an iterator of data frames in pandas. So these are not Spark data frames. And then what will actually return to you is another pandas data frame. So what is really cool about this is, or the most common way MapInPandas gets used is, first of all, you'll define your signature. So my function name is just my MapInPandas. Again, it takes in a iterator of data frames. So this dfs is an iterator, and then it's going to return back a pandas data frame. So first thing, most common pattern to do is actually iterate through the iterator of data frames. So we're going to perform basically data frame by data frame operations on our input. So our first for loop, so for data frame in the data frames iterator, and then we can actually start to do normal pandas operations. So again, there's so many things that are easier to do in pandas or even just generic Spark. And so that's what we're going to start to do here. So we can say, for every row in our input data frame, perform these certain set of actions. And you might only have one for loop, you might have two for loops, you might have three for loops, depending on what you're actually trying to do. But the most important thing is that at the end, you yield back every result that you're trying to process, right? So you'll actually use a Python yield statement to return these rows to the caller. And this is kind of what you get back from this function. So let's take a very basic example and see how this might work in practice. So the basic, first of all, pretend that explode is not an option for some reason. Explode didn't exist, or we have some kind of different example we want to try to do. Let's say that we have some incoming records. Each record has a unique ID, but in the actual contents of that record, for some reason, it contains two records in each input row, right? This is not super useful to process. We basically want to split it out to map these rows so there's one row per JSON payload. So let's actually jump into a notebook example and see how this works. As an aside, all of this code will be shortly available with an upcoming blog post, but we will share that later on, or keep an eye out on the Databricks blog for this. So just to show you the setup, how this actually works, we have a Python or a Spark data frame. You can see it's exactly like we showed on the slide. We have multiple, we have a list, or we have an array of JSON data, and we want one row back for each of these items in the list. So what would a PySpark or a MapInPandas function actually look like for this? So first of all, we'll kind of do our imports like standard. And then one of the important things when using MapInPandas is you have to define the return schema that the MapInPandas function is returning, right? It's basically this data transfer between pandas and Spark. So we have to be very explicit in the schema being passed between those two different types of data structures. So this is our return schema. This is super important when using MapInPandas. You kind of have to think ahead to what your function is returning and be explicit in defining this. So we'll just define this variable called return schema, and then you can see it is a Spark, struct type. It's the Spark style schema. Now we can actually start to write our function. So we will define a function called unpackJSON. And again, it's going to use this iterator of data frames and then return a pandas data frame at the end. You don't actually need all of this, to be as explicit as this, but it's good to kind of keep in mind. So what we'll do is we'll say for every data frame in our iterator of data frames, let's perform some row by row operations. So all we're going to do is iterate through each of the JSON items in my current row of JSON data, and then basically just parse that out as a new item or a new row. So basically we're saying row by row for each JSON item in each row, let's just create a new row and then yield that back to the calling data frame. And then we'll use this counter to kind of keep track of how many objects we've unpacked from each row. So that's as simple as this function is. You can see it can get a little bit complex. There's a couple things to keep in mind. We have 3 for loops in here. It's very common when using MapInPandas because you are trying to perform row by row or even some iterator within each row operations at that level. So just kind of got to keep track of what you're doing row by row. And then to use this, we will just call our MapInPandas function. So we'll pass in our data frame, right? If we remember, our data frame had two columns, the ID and then that JSON array. And then we'll call MapInPandas. The MapInPandas function takes in two things. One of them is our function, right? So this unpacked JSON is our function name that we're seeing right above here. And then the return schema. So when we run this, it goes pretty quick, right? It's a very efficient way to do row by row operations because basically one instance or the function runs in parallel across each core of your cluster. And what we get back is exactly what we expect. We basically unpacked this, each of the items into its own row, and we kept track of the row ID for each ID. So that's like as simple of an example as we can come up with to show how to use MapInPandas. But really the purpose of today is to show more sophisticated use cases of how we use MapInPandas. Before I move on, I'll just call out another thing that we'll see in a lot of the other code examples we're going through. Because of the way that data is serialized across the cluster, it can be very hard to parse the errors that happen in the innermost loop of our function. So if there's some error in here, right, if I'm making some external API call and I get, some, HTTP error in this section, it's very hard to kind of parse that out. So what we commonly do with MapInPandas is include try and except clauses. And in the try, this is kind of what we're actually trying to do. But then in the except clause, if we actually do get an error in this innermost loop, we'll actually use this traceback library to basically parse out the error that we're receiving back. So you'll see this throughout the rest of the examples. We'll see just this try except logic as well as use of this traceback logic. It's not super important for understanding how to use MapInPandas, really just a developer tool to make it easier to process or figure out what's going wrong in your logic of your innermost loop. So just wanted to call that out. All right, so skipping ahead, let's talk about a use case that we saw from a very large software company. So the use case for this customer is they were processing raw email text from a cybersecurity use case. So imagine that they have a S3 bucket on AWS, they're an AWS Databricks customer. They were receiving about 200 million emails per day into this S3 bucket. However, the upstream team who was providing these emails was not maybe using the most efficient data transfer format, or they were doing something convenient for them that may have been a little bit more cumbersome for downstream teams. So they provided these email files in zipped compressed tar files. So hopefully everyone's seen a tar file before. It's just a compression technique. And each tar file can contain many email files. So if you can imagine, the S3 bucket's actually receiving one big tar file, and each of these files might contain one email file, it may contain hundreds of email files. Really depends on the size of the individual emails within each tar. The kind of their constraint was that they knew that each tar would contain up to 300 megabytes of email files before the tarring occurred. So each of the tar files was smaller than 300 megs. And again, their production target was 200 million emails per day, right? So those broke down across a fewer number of tar files, but you can kind of get a sense of the data volumes we're talking about here. We're not talking about thousands or millions, we're talking about 200 million emails, 200 unique records basically to process per day. Total data volume size of that is much, much larger. So what they had tried to do initially, and we have a kind of a blog detailing out one of the issues that they had approached, is they had tried a combination of a user-defined function, so basically a row-by-row UDF in Spark, plus the explode command, which I mentioned earlier, which would take one input row and break it out or explode it into many output rows. But it resulted in crazy memory errors, even as they scaled up the node sizes, scaled to larger clusters. This just kept failing because basically each of these 300 meg files is the implementation that they had attempted just put too much memory pressure on the cluster. So this is kind of the setup. This is basically the problem we're trying to solve. How do we deal with, first of all, high volumes of input data, ingest this into a Delta table so we can actually perform analytics on it, right? So they had a lot of analysts downstream, other data engineering, ETL use cases that needed to take the contents of each individual email and perform some analysis for this cybersecurity use case at scale. So that's kind of the setup we're going to look through, and really, with all that background of MapInPandas, we can start to build a scalable solution to start to approach this. All right, so the first thing we have to do is also understand another feature in Spark and in Databricks, which is called Delta Live Tables. So this is not necessarily meant to be a Delta Live Table session, but what we'll do is go through an example, first using Spark structured streaming, and then moving on to Delta Live Tables to see how it all comes together. So let me hop back into my notebook example, and I'll come into the structured streaming demonstration. So just to give a sense of scale of it's obviously not real customer data. These are all fake emails, just a simulation of this kind of situation that the customer was experiencing. But we have an S3 bucket, and on this S3 bucket, we have a directory called tar files. And within this tar file, you can see we have many of these pretty large sized tars. So these are about 300, 400 meg total. So very, very large files to process. And importantly, Spark doesn't have a native codec to handle gzip compressed tar files. So we can't use any kind of out of the box function in Spark to process this particular file type. As an aside, the MapInPandas function, or the MapInPandas approach we're going through here, is super powerful for any arbitrary file format, right? Spark is limited to the number of types of file formats it can deal with, right? So you're working with Delta, you're working with Parquet, JSON, CSV, ORC, you're good. You don't necessarily need this approach, but that is a small subset of the universe of file types. So we've seen other customers implement this approach with proprietary formats that they use to transfer data internally, the latest, greatest new compression format that's been open source that hasn't made it into Spark yet. So really this approach that we're going to go through generalizes to all of those types of file formats. But in this case, we're just looking at tars. So after our import statements, we will define our MapInPandas function, right? So first step, we'll define our MapInPandas function. So what's really interesting about this approach is that within our MapInPandas function, we can use any type of arbitrary Python library, or in this case, we're using the Boto3 client library to actually go retrieve each of these file formats. So this is kind of not super intuitive what's going on behind the scenes here, but what we're doing is when Spark reads from a file or from an S3 location, the first read that occurs, it's not actually reading the files. It's reading the list of files that it needs to ingest. Right? So now that it has a list of files to ingest, it's going to use the Boto3 library to go actually grab the file itself and get it onto the local copy of the function to perform this unpacking. So what we're actually passing into our MapInPandas function is a list of files to go process, then we'll go retrieve them. So first thing we'll do is iterate through every data frame, and then for every row of our data frame, first thing we're going to do is kind of parse out our bucket name and the key of the object we're trying to retrieve from S3. And this is where our try and except clause comes in, super helpful for debugging. What we'll do is create basically a named temporary file using the temp file Python library, and then use the S3 client to download that file itself. Right. So again, one nuance here, when Spark is reading the S3 location, it's not reading the contents of the files. It's not trying to grab the entire file. It's just grabbing the key to the file, and then we're downloading it within the context of a single function. And this is a much more efficient way so that we're not transferring, 300 megabytes between workers of our cluster. It's just much more efficient to actually perform this operation to get the remote file from within our MapInPandas function. And then this is kind of where our custom unpacking. So we don't have to be an expert in this section, but there's some, you can go Google the tar file library, pretty easy to use, but we just use this kind of generic Python library to actually unpack and return each email file within it. So what we'll do is actually read the file data. We'll use this extract file operation and then return it or yield it to our calling data frame. So when we get to this point in our function, we have taken a raw path to an S3 object, grabbed that object, unpacked it, and for each object within that tar, we've returned it to our calling function. So this is kind of the very memory efficient way to handle this operation, because at the end, we'll just go ahead and delete that local copy of the file from each worker. And then we have, of course, our accept logic and then our schema. Again, really important. So what we're expecting back is the path to that object, the length of it, some way to keep track of the ID of each, and then the raw email. This is actually what we're trying to unpack. We have a column that's just basically the raw, a giant string, very, very long string of all the contents of each email. So how this actually looks when we do it just in regular Spark streaming, we'll first of all define that a variable called tar source, which is just our S3 path. And then we'll use some really cool functions within structured streaming. And in Databricks specifically, we'll use a feature called autoloader. So if this is the first time you're seeing the cloud files format in a Spark read or read stream command, what this command is basically doing is saying, we have some cloud storage location. In this case, it's S3. It could be Google Cloud Storage, could be ADLS. And we're receiving new files at this location. If you think of any type of data engineering use case, basically the first step is to ingest the data, and cloud files makes it super simple on Databricks. So we're basically saying read stream, we have some cloud storage location, and at this location, we're receiving new files. We want to ingest each one of those files exactly one time. We want to make sure we don't ever duplicate a file ingest. And the way this works on Databricks is we handle all of the logic behind the scenes. So there's kind of a few different ways you can set up cloud files in autoloader. There's one where you'll list out all the items on each directory, which works for smaller numbers of files and sub-million files. But there's another type of approach called file notification mode, which uses the cloud primitive file arrival notification. So basically, anytime you can set up on AWS, anytime a new object hits an S3 bucket, you'll basically ping that file arrival event, and Databricks will set up all the infrastructure behind the scenes to kind of keep track of that for you. So in this case, we're using file notification mode with autoloader, which is super powerful way to scale to hundreds of millions of files arriving every day, which is kind of the use case we're dealing with here. And so that's kind of all we're doing at this point in the code. And one important thing is we're treating these tar files as a binary file format. So you could specify anything you wanted in here. So if these are Parquet files, if these are JSON files, you can specify that. But in this case, we're going to treat our tar files as binary files, which is kind of just a generic catch-all. If we can't necessarily process it with Spark directly, we'll just treat it as a binary file. And then all this is really doing is just giving us a list of all the files to process. So when we run this, we get a few things back. All we're going to do is use the path. The path is just the S3 key. And then a few other things. And then we'll basically split out that path to get the bucket name and the source key of each file. So you can basically say, hey, we're going to split just the bucket name. So here's my bucket name. And then the rest of it will just be the key that Boto3 library needs to go retrieve each individual file. So with this, once we get to this point, we basically have a list of potentially hundreds of millions of files to go ingest from S3. And then we haven't retrieved the data itself. We haven't retrieved the files themselves. We just have a list of object keys on S3 to go process. So then what we'll do here is actually do the file retrieval and unpacking of each of those files in a single step. So MapInPandas here, we're going to pass in that S3 untar function we defined above, actually doing the unpacking. And then we do the return schema. So again, this is the schema we're expecting back from our S3 untar function. So all said and done, right? We set up our Spark read stream operation. What we have back is a data frame, and I ran this a little while ago, but you can see for each of these objects, so this emails tar or emails _8 file, we have unpacked multiple records, right? So there's record ID 1, or record ID index 0, record ID 1, and then we kind of do a substring to take a look at the contents of the raw email. So it's kind of, you can tell it's just totally randomly generated email, but we've just taken the first 100 characters of the contents of each very large email string. So, for this customer, for this use case, one of these emails could be, 300 megabytes long. It could contain, attachments and images in binary format. It could contain all kinds of things, but they just wanted to treat it as a giant string, and then downstream logic would actually make, parse it, parse out the from, parse out the to, parse out the subject line, and all of that kind of stuff. But they just wanted it first as one giant email, or one giant string containing the entire contents of the email. So in this case, each of our emails looks like they contain each of our tars looks like they contain 2 emails, but this would work just as well with, if a single tar contained hundreds of emails. So that's kind of the basic approach here. And once we have these 2 kind of fundamental items, right, we've seen how to use autoloader, right? This is a really important part of this, is that with autoloader, we're only getting the file paths back, which we see here. And with this, we're actually not performing a get operation on S3, right? So an important thing to consider when you're reading from S3 or any cloud storage location, for each get operation, each file you're retrieving back, there is some cost incurred with that. I think on S3, well, I don't want to quote any rates, but per 1,000 get operations or 10,000 get operations, it's some cost to that API interaction. So with this operation, we're not actually getting each file at this stage. We'll do it once with the Boto3 library in our MapInPandas function. Right, so this is kind of the building blocks of a Delta Live Tables pipeline. Let me just flip back to that so we can actually see what this looks like. All right. So if you've not seen Delta Live Tables before, Delta Live Tables in Databricks is a declarative ETL framework for defining data pipelines. So in this case, what I've done with Delta Live Tables is create a pipeline called uncommon file formats. And with this pipeline, I have set up a few different things. So the different product editions that allow you to do different types of data engineering tasks. So for example, I'm just doing the core product, but with Pro, you get features like change data capture and ability to use the apply changes into API. With advanced, you get data quality rules, so you can do row by row Boolean logic of enforcing data quality. And there's a lot of nuance between the 3, but I'm just using core for what I'm showing. And then really importantly for this use case is the pipeline mode. So the way Delta Live Tables approaches things is is something streaming versus batch. Delta Live Tables allows you to kind of dial the knob for right time processing. So when our pipeline mode isn't triggered, some scheduler or some human has to actually trigger the pipeline to run. So if you had a use case where, hey, the analysts only need this data at 8 a.m. every day, and no data has changed since the last time the pipeline has run, or we don't need it more frequently than that, you may leave it as triggered. But if you want to change it into continuous, you just flip the switch to continuous without any code changes. So Delta Live Tables allows you to, with zero code changes, change the latency of a use case from batch to essentially real time very simply. But I'll just leave it in triggered mode for now for demonstration purposes, but very easy to switch this continuous. And in fact, this customer did, because they wanted to process files continuously throughout the day as they arrived on S3. The source code for our Delta Live Tables pipeline is just a single notebook. So this notebook I'll flip to in a minute, but you can actually have multiple notebooks as part of a pipeline. They can be combination of SQL code versus Python code. And it's pretty intuitive to define the logic of the tables you're trying to create within each language. Our destination in this case for demonstration, I'm just using a legacy Hive Metastore table, but of course Unity Catalog is in preview right now, soon to be generally available. But you can actually publish these tables to a Unity catalog so other folks can consume them. And all the tables in my pipeline would publish to this target schema. So this is just the database or the schema name where I want these tables to be queryable. There's a couple other settings around our compute. I'm just using a fixed size for demonstration purposes. For actual production workloads where you might have bursty data volumes, bursty file arrival, we definitely recommend enhanced auto scaling as a very efficient scaling algorithm, so it will match the input load very well. But for demonstrations, I just wanted fixed size cluster to know exactly how much it's going to cost. And then I'm actually using photon acceleration, which allows more efficient processing and reducing the total cost per workload. And then there's a couple other settings. I actually passed that S3 path as a parameter in my pipeline configuration. So this is a good way to do this, to parameterize your pipeline. If I need this, if I had 2 S3 buckets that I needed to run this on, I could make a clone of this pipeline, change the setting, and the code underlying the logic wouldn't need to change at all. So there's a great way to parameterize each of your pipelines using this type of configuration, just as you would in any production job. All right, so with that setup, we can actually take a look at what's happening behind the scenes here. So the most important part of this is the logic defined in my source code. So let me actually click into the source code link, which will take me into a notebook, which again, this should be published soon. But I'll actually flip back to this view. So when you're using Delta Live Tables, when you're using a notebook as part of a Delta Live Tables, you get this nice kind of interactive kind of command center of what is happening with your code. So you can see, because I've run this notebook as part of a Delta Live Tables, the notebook has awareness to that. So I can actually see what live tables it's being run as. If it's attached to multiple, it will show multiple. And I can quickly jump to it, view logs, and then once I have done a run, I just kicked off a validate operation. It will actually show all of the event logs. I can see any errors. If I have any syntax errors or processing errors, it will tell me that. And then it will tell me all of the update details as I run this over time. And I can actually start to see a graph of how the tables are created. So I can actually see my DAG of which tables are dependent on which other tables within my pipeline. So it's super handy, kind of accelerating development with Delta Live Tables. If it's not available in your workspace yet, it will be soon. As soon as you attach a notebook to a Delta Live Tables, this should become available within the UI. So as that validates, I'll kind of go through the logic. A lot of it should look very familiar. First thing we have in our DLT notebook. So this is the notebook our DLT pipeline is actually running. So 90% of it looks identical to what we just looked at in the streaming example, or kind of the raw structured streaming code. So I have my same S3 on tar logic. This should be completely unchanged if I remember correctly. I haven't changed anything for my test code. And I have my return schema that I expect. And then the only change with the Delta Live Tables pipeline is, instead of just running this Spark read stream and then displaying that data frame, we're actually going to wrap this in what's called the DLT decorator. So first of all, I'll import my DLT library. So DLT, Delta Live Tables. And then to tell DLT that something I'm defining here is an actual table that I want to materialize, you can also use views in DLT, where it just creates kind of a logical view rather than materializing or creating a copy of the data in Delta. I'll just use this @DLT.table decorator. Within this decorator, I can do a ton of different things. I can set my partition scheme. I can define a schema if I want. I define data quality rules. There's a lot you can set in here, but in this case, it's pretty basic. I'm just giving it table properties to allow the reset to occur in this demo. The next thing I'll do is actually define a function that returns a Spark data frame. So this is in Python, we actually define a function that returns a PySpark data frame. It can be a batch, the result of a read operation. It can be a read stream operation. In SQL, it's a little bit different. The syntax, you'll actually do it's almost like a CTAS, a create table as select, but it'll be a create live table as select, and then you define your query logic. The important thing is, one thing to note is that what we're returning from our function does not include the write operation, right? So all we're doing is the read part of defining a structured streaming query, not the write. Delta Live Tables, the framework, will handle the write portion for you. Figure out if it's an append, if it's a complete. It will figure out the materialization strategy that's most efficient to handle the logic you've defined. So the only thing I'll do in here is retrieve that tar source. This is just that S3 path that I defined in my pipeline configuration, and then identical logic to what we saw before. This is just the same spark.read stream, and then I'll just wrap it in this return statement so that DLT can use this structured streaming data frame as part of the pipeline. Let's just make sure that this validated properly. Yep, so what we see when we click the validate operation at this for this pipeline is it confirms like, hey, all of your logic is correct. There's no syntax errors. This is all possible to run as part of your pipeline. It's kind of just a data quality or a code quality check. You can see like the schema of the return table makes sense. That's what you're expecting. So it's just a nice intuitive way to confirm that everything will work once you click go. So I could obviously click start from here and it would start processing a new batch. But let me flip back to the pipeline itself and we'll show how to do that. So one other nuance to Delta Live Tables is there's two different modes for developing a pipeline. So I'm in development mode right now. So what development mode means for Delta Live Tables is it is it's going to keep a cluster around between each time you click start. So again, this is a triggered pipeline. So there's nothing running continuously, but in continuous, it would do the same thing. Continuous will basically say, hey, if there's an error, the cluster is going to stay warm because we're expecting you're watching this, you're iterating through your code, defining your logic, and you're going to actually pay attention. The cluster will auto-terminate after some time, but it will kind of be interactive that way, just like you would on a normal notebook cluster. With production will not keep the cluster alive between updates. So it basically says this is a production job. If you have some error, you would set a notification, right, that says, on a failure, we want to go page somebody to come look at this. But between that time that the cluster fails and someone resolves the issue, the cluster goes away. So there's no cost incurred. by resources waiting around for somebody to come fix your code. So that's kind of the difference. Development, obviously what it sounds like in development, you should be using this because it's much faster to iterate through your code. And then in production mode, it will kind of retry if there's some cloud availability issue, but if there's errors in your actual logic or your data, it will kind of fail. So you're not getting billed for that idle usage. The other thing we could do directly from this pipeline is define a schedule. So really nice is these Delta Live tables can be integrated with the workflows scheduler in Databricks. So really simply, I could say, hey, I want this to run, emails, ingest. I want this to run every day at 10:40 a.m. and I want to be alerted in case it fails. And then once I click create, it's going to create an entry in the workflows tab, and I can actually see that my task as part of this is just a Delta Live tables pipeline. Once I've done this, I can actually add other dependencies, or if I have a precursor step, right? If I have another job that needs to run or another job that needs to run after it, I can build that. I can actually build in if-else conditions as part of this workflow orchestrator. So it's just a very powerful way to build very complex ETL processes or data processes. One nuance to this is you'll start to see some differences, or you'll start to visually see similarities as you use Delta Live tables, that I can have multiple tables pointing to each other that are dependent on each other. The way to think of Delta Live tables is as a data flow orchestrator, right? So I want to create table B dependent on table A. Table A ingests all of these files from some cloud storage location. So it's kind of the way data flows between table objects or view objects. The way the orchestrator works or workflows works in Databricks, each of these is a kind of a task orchestration that may produce different data flows, but it's kind of a higher level concept than a single Delta Live tables pipeline. So the nice thing about it is with workflows, you can orchestrate DLT pipelines, actually triggering this to run and generate a data flow, but I can also have other notebooks or other Spark submit, or I can refresh a dashboard afterwards. I can build really complex kind of orchestration processes using the workflows side. So I just want to add a little bit of nuance. It's pretty easy to schedule as a job. Let me actually remove that schedule or pause the schedule so it doesn't run. But just something to call out there. So what have I actually done when I last ran this? I basically created, I did a one-time run. I basically said, do a full refresh that will ingest all of the data that's available on that S3 location. After I run it the first time, what I would do is actually click start, or let my schedule click start, and it's going to ingest any new file that has arrived in the last, since the last time the code ran, right? Because it's a streaming table, right? This is an important nuance with Delta Live tables. Because it's a streaming table, it has state. A streaming table knows what data has already been ingested and will only reprocess or process the new data that has arrived. So it's a super powerful way to really efficiently get exactly one's processing, whether that's from Kafka or any other streaming source, another Delta table outside of the pipeline, and in this instance, an S3 location that's continually receiving new tar files. So what we have here is once we've run this, we have a table that's immediately queryable. So as soon as this process finishes, right, it took less than 2 minutes to process like a couple gigs of tar files, do all of that unpacking. We have a table that's queryable. And let's see if this will load. Some of the email strings are very, very long, so the UI typically has an issue. But we can see, any other user would be able to query this to go, refine it, to extract values, perform analytics on it. We basically have a pipeline that will be scalable to millions or hundreds of millions of files arriving per day. That kind of, we can flip into production mode and make this pipeline available, or make this data available for all of our downstream use cases. So that's kind of the recap or the the use case we wanted to cover today, 45 minutes, covered a lot of ground. In this, we showed how to use MapInPandas as a function, how to define the function signature, how to use it on Delta live tables, and then what it actually looks like to use Delta live tables with a job orchestrator for this type of use case. So it doesn't end here. Again, Delta or MapInPandas is a super flexible approach to do this type of yielding more than one row per input row. And our blog post that's coming out soon, I don't have an exact date yet, but keep an eye out on the Databricks blog to have these code examples handy. They'll be published along with the blog and runnable in any workspace, including these tar files, like scripts to generate the tars. So I'll end it there, and we'll see if there's any questions related to this or really anything in general that we can cover in our skill builder session today. So Dallas, have you seen any questions come in?
Yeah, I don't see any questions. Feel free to put stuff in the chat, or if you raise your hand. There you go. There's a question on sharing the cluster config. Is that something that we're open to doing?
Yeah, absolutely. I can flip to that real quick. Yeah, so get back to the pipeline. So when you define, I assume the question was about the Delta Live Tables pipeline config. So with Delta Live Tables, a lot of the cluster config is managed for you. So really the only options you have when selecting your compute, you can use a cluster policy if that's been defined for you. When you define the cluster policy or an admin defines it, they can specify, hey, this policy is allowed to be used for Delta Live Tables. And you can see I have a lot of policies available here. But really the only settings you need to worry about are the enhanced auto scaling or fixed size. So really the only two we recommend. Enhanced auto scaling works for really bursty workloads. It's a better scaling algorithm or a more sophisticated scaling algorithm than like the interactive or notebook auto scaling. So it's much more performant. Fixed size you would use if there's like a limited cost or you don't have really tight SLAs for processing arriving data. And then you can say like the max workers or the scaling bounds there as well. So of course you can do other things with this, right? You can see I've assigned an instance profile, and anything you can do on a normal cluster, you can do on a Delta Live Tables cluster. The UI is intentionally very plain, but if you flip into the JSON view, we can see, in this case, I've added an instance profile to access that S3 location. I've actually specified some Spark configurations so that optimize writes with Delta don't happen, just based on my very long strings in my emails. And I think that's basically the only thing I've set on my cluster. But with your pipeline, if you flip into the JSON view, you can modify any of the parameters in the cluster settings. So it's not even worth it to share these because these are all very basic. But you can go ahead and modify these.
Thank you.
Sure thing.
Any other questions? Another minute in the chat. Or if you want to raise your hand and ask directly, you can. All right, I don't see any other questions. So with that, TJ, I'd like to thank you very much for your time, and for the attendees, thank you very much for your attention. It's great seeing you, and this will all be posted to a YouTube channel. Look for that notification to come out shortly as well. But thank you very much.
Thanks everyone for your time today.